This video is going to continue the Power Series exploration. In the later part of the Power Series, and we're now looking at, I think we're somewhere around number 7 in the packet, we're going to start to look at the idea that you can take known power series for known functions, and you can take other functions that are very close, or other series that are very close, and you can algebraically manipulate those to get series representations of other similar functions, okay? And that's really what the focus is going to be in this class. We're going to look at several different series for several different types of functions and see how we can kind of tweak and wrangle those things into matching others, other functions. All right, so here's what we have currently. We know that the series, the power series from n equals 0 to infinity of x to the n would generate 1 plus x squared plus x cubed and so on. That's actually a geometric series with an r value of x, or multiplied by x each time. And we know that this is only going to be convergent. It's only going to have a sum if x is somewhere between -1 and +1, okay? And we saw on a graph, as you write out more terms of this series, it will more closely match the function f of x equals 1 over 1 minus x for values between -1 and 1. And again, as you go farther and farther out, you get closer to that -1 to +1 range, okay, as you write more terms out. And by the way, if you think about just putting individual values in here, you know, for example, at 1/2, you know, if you had 1 plus a half plus a fourth plus an eighth plus a 16th plus a 32nd, you're starting to get really, really small values as you get farther and farther out. And so, you know, you might look at this and say, wait a second, there's supposed to be infinitely many terms. You know, there's supposed to be an x to the 40th power term. There's an x to the 250th power term. There's an x to the 10 millionth power term. However, again, with most of the types of values we're working with here in the range, you only need to go out 4 or 5 values, and you're going to be really close to what the actual sum would be for any particular value of x that you substitute in. So that's something you always want to keep in mind. Most series, if you write 5 or 6 terms out, it's going to come very, very close to what you're trying to represent. All right, so down here I have a series that looks a little bit like this series, but not quite. Notice it's 4 plus 4x plus 4x squared plus 4x cubed and so on. And hopefully you notice here the only difference between this series and this series is that the lower series got multiplied by 4, okay? Because every single term in this infinite series has been multiplied by 4, we can factor out a +4, okay? And we could basically, again, factor 4 out of each of these terms, and we could say, hey, I'm going to take this infinite series and I'm going to multiply this infinite series by 4, and that's another way of representing that series, okay? You can factor a constant out of infinitely many terms, all right? If you take a look at what we have here, this is the series representation that we had up here. This is the series representation for 1 over 1 minus x. So this is just 1 over 1 minus x. The whole thing is being multiplied by 4, and so it's really just going to be 4 times 1 over 1 minus x, which means the new series that we're representing, I guess I don't want to call it f, maybe I'll call it g of x. That new series that I was representing is 4 times 1 over 1 minus x, or 4 over 1 minus x, all right? So that's the basic idea there. And, you know, so if you can tell, hey, the series just got multiplied by a value, all you need to do is multiply by that value and you'll get your new equation. So I want to look at a couple of other possibilities that you could see. So let's say that you're given a series representation, and let's say again that it looks real close to this, but not quite. Maybe it's x plus x squared plus x to the 3rd plus x to the 4th, and so on. And you look at that and you say, this series here looks a whole lot like this series up here, except each of these terms got multiplied by an extra x. 1 times x is x times x is x squared times x is x cubed, and so on. You can also factor a variable out. Okay, so I could say, all right, I'm going to factor an x out of each of these terms, all right? And so if I factor an x out of each of these terms, if I divide this by x, I'd be left with 1. And again, I'm factoring an x out in front of parentheses. If If I divide this by x, it's x to the first. If I divide this by x, it's x squared. If I divide that by x, it's x cubed. And notice what I've got then. I have x times the same series that we have up here. All right, and so as a result, this of course is going to be 1 over 1 minus x. The whole thing was being multiplied by x. And so the new series that we would end up getting is the series x over 1 minus x. That would be the function that would be represented by x plus x squared plus x cubed and so on. Okay, it's the same series we had before, except multiplied by x. And so, you know, if you had a series, again, if you had a series like x cubed plus x to the fourth plus x to the fifth, and so on, maybe you would notice that this whole thing got multiplied by x cubed. Okay, so you could factor an x cubed out of this, and that would drop this down to an x, and that down to an x to the first, and that down to an x to the second, and so on. And it's going to be x cubed times the 1 over 1 minus x function. And of course, that's going to be x cubed over 1 minus x. Or, you know, maybe it was, you know, 4x to the third. Oh, I'm sorry, that should have been 1 there. You know, if it had been a 4x to the third, and 4x to the fourth, and 4x to the fifth, maybe it would be a 4x cubed over 1 minus x. So check, if you see a series that looks like you just multiplied by something, typically you can just divide that out, and you can multiply it by the original series and get the new function that was being represented by the series that you were given. Okay? Now, there are other things that you can do as well. For example, you can also substitute values in for x. For example, let's say I didn't want to represent 1 over 1 minus x. Let's say I wanted to represent 1 over 1 minus 2x. Okay, something like that. The form's always the same, okay? It's 1 over 1 minus your input value. Okay, if you were putting 5 into this function, it'd be 1 over 1 minus 5. If you're putting 10 into this function, it's 1 over 1 minus 10. Okay, this is just like you're putting 2x in place of x. Okay, and so because it's going in place of the input, you could literally just replace each of these x's with a 2x. Okay, this is really going to be f of 2x is really what you're doing here. Okay, you're putting 2x in place of the x. Okay, well, what would that series be? That series would just end up being 1, doesn't change. You're putting 2x into the function in place of your x, okay? And then you're putting 2x in place of the function, okay? Notice the input here is being squared, so you're replacing the x with a 2x, and that whole thing that you replace the x with is still being squared. And then you put a 2x in place of the x there, and the whole thing's being cubed. And you can write this different ways. You could write this as 1 plus 2x plus 4x squared plus 8x cubed, and so on. You can also still write this using summation form. And sometimes it's going to be easier to look at the simplified version. Sometimes it's going to be easier to look at the unsimplified version. I think in this particular case, it would be easier to look at the unsimplified version. So notice you're putting x in each of these spots each time, so you have an x to the n power. We were putting 2x in as the input each time. So instead of x to the n, it would be 2x raised to the n power, okay? And so you can see 2x to the 0 is 1, 2x to the first is 2x, 2x squared would be 4x squared, 2x cubed is 8x squared, and so on. So we can say the general term for this series, this would continue out to the term 2x raised to the n power, or you could distribute that. You could write it as 2 to the n times x to the n if you wanted to write it that way too. And you might notice that if you were noticing that these were powers of n. So, you know, sometimes it'll be easier to write the general term from this series. Sometimes it'll be easier to figure out what your overall pattern is before you simplify it. Just different types of approaches, okay? So I'm going to delve a little bit more deeply into this, but I think I'm going to do that in another video coming up next.